Welcome my friends, welcome to my next lecture. In my last lecture I talked about, given a complex number, non-zero complex number, what is the small arg of z. Now as I said, in this lecture I'll start talking about what is is there any kind of what is called okay, small arg of z is a like multiple valued functions. Can I have a out of multiple valued functions, can I have a single valued functions? So and answer is yes, and it will give you a kind of notions of what is called principal argument of a non-zero complex number. So I will start with this concept, and then if time permits, then I will talk about like various properties of complex number or nth roots of unity, and later on I will talk about what is called topology, because distance I already discussed in the complex number. So topology like the open set and closed sets, so on and so forth. Okay, so as I said, so now I am trying to, or I should define the concept of what is called, you see I have written, this is what is called principal value, sorry, this is the what is called principal value of argument of z, that means capital arg of z. Earlier one, given a non-zero complex number, you have a small arg of z. Now this time, given a non-zero complex number, I am going to define what is capital arg of z, and that is called the principal argument of my complex number. Okay, what is that? You see I have written. So picking one of the values of your set function small arg of z for computation purpose. What is that? Okay, for example, suppose I'm giving you some conditions. Okay, so if teachers give some conditions, and I'm asking that all students should be able to pick up the same and the unique value for this small arg of 1 plus I, and how do I do that? So that means there should be a way, like you have a set valued functions, you have a multiple valued functions, but is there any way to make it into single value? That's the question I'm asking. So an answer is yes. How to do that? You see, I'm saying that restrict the value of small arg. Small arg is a set value, right? You have many values are there. You take the values from the set small arg of z which lies in the interval minus pi to pi. This is my rule. Okay, so that means you cannot take any arbitrary values from small arg of z. You should pick that value in your set small arg of z which is lies in the interval minus pi to pi. And now tell me what is the argument or capital arg of 1 plus I. Then you can easily calculate. Like in my last lecture I calculated what is the 1 plus I. If I have this complex number, what is the argument? And if you just remember in the trigonometric form, so you have a cosine of theta which is I think x by r. That is x is 1 and r is square root of 2, and it will give you your theta is equal to what? Pi by 4, and pi by 4 lies in here, right? So if you have interval minus pi to, so that means this is minus pi to here. Okay, so then these values, and pi by 4 is sitting inside. So therefore I can say that yes, so if I follow this rule, then my this arg of 1 plus I, so that means what? So if you remember, what is the then in this case arg of what is 1 plus I? This is pi by 4 plus, if you remember in my last lecture, so this should be 2n pi where n is running over z. So this is the set value, right? So out of this set value, which value, so if you pick one value which should lies in this interval, and this is exactly your pi by 4. Yes, that is. So and that pi by 4 I'll call that this pi by 4 as capital arg of 1 plus I, or this is called the what is called principal argument. So therefore, given a non-zero complex number, given I should take one value from the small arg of that complex number which lies in minus pi to pi, and I am saying that value is the principal argument. Okay, so I have written clearly. So for each non-zero z, there is only one value, that is very important. There is only one value of the set small arg of z. Let it be this theta, and which lies in the interval minus pi and capital pi, right hand kind of point is closed. This value will henceforth will denoted by capital arg of z, and this is called the principal value of my argument arg of z. Okay. One example, like for example, if you remember, I calculated what is small arg of 5. If you remember, so what is my 5? So this is my complex plane. This is my point 5. So what is if I have a trigonometric for polar form, what is that? This is 5, 0, right? So 5 is the modulus, and since it is lies in the positive real axis, angle is 0. But what is the small arc of set? Small arc of 5. This is nothing but 2n pi, where n running over z. So if you remember, this is the set. Out of that, I have to pick one value which lies in the interval minus pi to pi, and which value? Only n is equal to 0. So that means 0 will be there. So therefore, what is my out of that, what is my capital arc of 5? This should be actually 0, and that is there. Similarly, you can calculate what is capital arc of I. So what is the point I? I is here actually, right? This is the point I. So this is 0, 1, and what is the angle? Angle is pi by 2. Okay, so you can do that. So therefore, capital arc of pi is pi by 2, and you calculate this is the object. Okay, so these are the examples. So therefore, you just try it, take one complex number, find the angle theta, and choose the angle theta which lies in the interval minus pi to pi, and that angle I am saying that principal argument. Okay, okay. So now, as I said, so earlier I have z goes to small arc of z. This is a set valued function, so I cannot do any analysis there. So now I have a z which is of course a non-zero complex number. Then I am defining what is called a single valued function. Now this is single valued functions. So therefore, as I said, once I have a functions, then when I will talk about the concept of limit, continuity, and differentiability, those concepts you are familiar with in the real analysis. Similar kind of concept I will talk about in the context of complex valued functions of complex variable. So therefore, since it is a complex valued functions of complex variable, so therefore I can say that, can I talk about continuity, or what is the largest domain in the complex plane such that this function z goes to capital arc of z, I can talk about the continuity of that functions. So this function I cannot talk, this is the multivalued function, so I cannot do that. So now once I have a single valued function, so therefore I can talk about the continuity of those kind of functions. So when I will talk about the concept of continuity, there I will talk about that what is the largest domain in the complex plane, so that I can talk about argument is principal argument is a continuous function. Just as one kind of observations, you may also think about that. You see, so what is the interval I am considering? Minus pi to pi. So that means, so I am coming from here and I am almost reaching to that negative real axis, but I am not crossing it. And that's the interval I demand that my principal argument. Okay. So what will happen in the negative real axis? You see, I am minus pi is open, so that means I am not touching my negative real axis. I am keeping open it. So I am not touching. So therefore, very near to the negative real axis, I am starting, and then I am coming back to the again very near to the negative real axis, but I am not crossing it or I am not touching it. So it is expected that when I will talk about the largest domain in the complex plane where my function z goes to capital arc of z is, or principal argument of z is continuous, you will see if I take out the negative real axis from the complex plane, the functions z goes to capital arc of z, it is actually continuous. The moment I will cross negative real axis, it will have a jump. So therefore, you kind of lose the continuity in the negative real axis. You will see. Okay, the moment you will cross the negative real axis, you will have a jump. So therefore, your function z goes to capital arc of z is not continuous. So the largest domain in complex plane is that you consider the domain C minus the negative real axis. That means C minus all those z where z is x plus iy. Okay, but negative real axis. So that means okay, so y is 0. So therefore, x is less or equal to 0. This kind of things. So z is equal to x plus iy. So okay, so you can say that. So this is the domain C minus all those z x plus iy, okay, where y is equal to 0 and x is negative. Negative real axis including the origin. So that means, therefore, if I have a what is called so if I have a complex plane, if I take out whole negative real axis include the origin, that means there is a cut in the negative real axis in the complex plane. There you will have the continuity of your complex functions. Z goes to capital arc of z. Okay, so maybe I will talk about later when I will talk about the continuity in general functions. Okay, so of course now you can easily guess what is the relations between small arc and capital arc. So I don't have to explain too much, because small arc is nothing but you just take the principal argument and you perturb by 2 pi k, where k is an integer. Okay, so this is, so once I have a principal argument, if I perturb it, then I will have the full small arc of the complex number z. But this is very nice actually. It says that okay, so if someone will ask you, okay, take this non-zero complex number, what will be the what is called principal argument. So this is the formula you should always remember. So given a complex number, how do I calculate the principal argument? That means you have a small arg of z, no? So that is okay. That means you have a theta, and if just part of it 2k pi, then the one small argument say that you can get it. But the question is, which theta should lies in minus pi to pi? So there is a formula. If you know this formula, then you can easily calculate, given a non-zero complex number, what is the principal argument. Okay, this is the just kind of calculation purpose or computing purpose. So I am writing computing principal value of an argument, or principal argument. Okay, so start with a non-zero complex number z. So first what you have to do, so you consider this z is equal to x plus iy. Since z is non-zero, so x plus iy is non-zero, so of course tan inverse y by x you have to calculate. So you get the tan inverse y by x, and you can get the principal value of tan inverse y by x, let it be phi. So and I want, or you should calculate phi, which is nothing but the principal value of tan inverse y by x, that you can do that, which should lies in the interval minus pi by 2 to pi by 2. Okay, so you have a z is x plus iy, get the principal value of tan inverse y by x, let it be phi, and I should say that you just take that phi which lies in the interval minus pi by 2 to pi by 2. Once I have that phi, then you have a x comma y, or x comma y, or x plus iy. It will be in a complex plane, or you can think about it as a point in R2. Now in R2 you have a fourth quadrant, first quadrant, second quadrant, third quadrant, fourth quadrant, depending on the like sign of x and y. So which quadrant, depending on the sign, you can have a formula. What is that formula? You see I have written with the value of phi, with the informations of sign of x and y, that means which quadrant it lies. Based on that, your principal argument formula will be like this one. It says that if I have x plus iy, if just x is positive, that phi, which is nothing but the principal value of tan inverse y minus y by x, which is lies in minus pi by 2, this is the corresponding principal argument. If x is negative, y is positive. X is negative, y is positive means what? X is negative means I am here, y is positive means I am here. Oh sorry, not here, here, only in that one. Then it should be, you put up phi by pi, okay. If x is negative, y is negative, then so on. So that means I am in the third quadrant, okay. X is negative, y is negative here. So that means you just take phi, which you already know, which is the principal value of tan inverse y by x, which is lies in minus pi by 2 pi by 2, then you consider phi minus pi. And if x is 0, that means this is x is 0, y is positive, that means I am in the imaginary axis, this is pi by 2. If x is 0 and y is negative, that means negative imaginary axis, it is minus pi by 2. Okay. So this is the formula. This formula will be very useful to calculate, given a complex non-zero complex number, what is the corresponding, what is called principal argument. Okay. So this formula you should remember. And this of course relation, you know, that is a relation of small arc and capital arc. Small arc is nothing but capital arc plus 2k pi. Okay, so this formula you should remember. So what is the formula? Given a complex number z which is non-zero, first you calculate phi. What is phi? Phi is the principal value of tan inverse y by x, which is lies in minus pi by 2 pi by 2. That you can do that. So first calculate that phi given a complex number z which is x plus iy non-zero. Then depending on that x comma y, it should lies either first, second, third, fourth, any one of the quadrant. Depending on the sign of x and y, you will have this formula. Okay, so you remember that formula. So given a complex number, then you will be able to calculate what is the corresponding principal argument. Okay, so then there is another form, what is called exponential form of a non-zero complex number. And what is that? It says that, so suppose you have a non-zero complex number z, Cartesian decomposition is x plus iy, a Cartesian form, can be written in terms of trigonometric form, I already discussed, which is z is equal to r times cosine theta plus I sin theta. What is my r? R is the modulus of the complex number, r is the modulus, and theta is the corresponding argument. Okay, but you know there is a formula called Euler's formula. What is Euler's formula? I think you people are familiar with. Euler's formula is e to the power I theta, which is cosine theta plus I sin theta. That formula you know, that is called Euler's formula. Once I have this formula, where theta is measured in radians, then I can write this complex number as z is equal to r e to the power I theta. using Euler's formula. And say if z is non-zero, then using Euler's formula I am writing my z, which is equal to r times e to the I theta. What is my r? R is the modulus of the complex number. What is my theta? Theta is the argument, okay, where r is mod z and theta is argument of z, which is known as the exponential form of the given complex number z. For example, if I have 1 plus I, what is the argument? Argument is pi by 4, and what is the modulus? Square root of t, so square root of 2, so therefore your what is called exponential form is square root of 2 times e to the power I times pi by 4. Similarly, you can just calculate minus I, which is what is the modulus? Okay, so you can draw what is minus I. So this is the point minus I. Okay, what is the modulus of minus I? So this is actually 1. So therefore r is 1. And what is theta? Theta is the angle. Okay, so r comma theta polar representation. So therefore, and I want the theta means, like if I calculate the principal argument, that is also okay. So for principal argument of minus, you calculate it, okay, this is actually turns out to be minus pi by 2, because this is the point you can easily guess. Therefore if I start from here, so it will be opposite direction pi by 2, but then since I am coming in the anticlockwise direction, that means it should be minus of pi by 2, okay. So therefore minus I, it is r e to the I theta, r is 1, e to the power I theta, what is theta? Theta is minus pi by 2. So therefore this is I times e to the power minus I pi by 2, and this is the one, okay. Similarly this, you can do that. Okay, so this is complex exponential form of a non-zero complex number, but there is a kind of concept is there. I am telling you, look, so this is, I am assuming that e to the power I theta is equal to cosine theta plus I sin theta, that formula, this is the Euler's formula. I am assuming it. With that assumption, I am saying that each complex number z which is non-zero, it will have a form r times e to the I theta. But you see, if you just kind of think for some time, look at the right hand side. Now given theta in radians, yes, so cosine theta is a real number, right? So therefore this is belongs to r. Sin theta, this is also r. So you have a x plus iy. So the right hand side is a complex number, perfectly all right. Because if I have two real numbers, ordered pair x comma y, then x plus iy or whatever it is a complex number. I said either you can write x comma y or x plus iy. So the right hand side is perfectly all right. It is a complex number. Now look at the left hand side. I am saying that Euler's formula says that it is of the form e to the power I theta. Now you can ask one question, sir, we are comfortable with e to the power x where x is real, right? Yes. So it is a formula. I know that Euler's formula is e to the power I theta is cosine theta plus I sin theta. But suppose if I would like to get the meaning of exponential functions, but e to the power x is real number, that I know meaning. But what is the meaning? Because theta is real, so what is I theta? That is also a complex number, right? I theta is also a complex number. What is that complex number? This is 0 plus I times theta, na? This is a complex number, x plus iy. So therefore, you are actually trying to say that e to the power z. But I know the meaning of only e to the power x. So what is the meaning of e to the power z? So later on, when I will talk about what is called analytic functions or power series, when I will talk about, then I will have the meaning of e to the power z. So given a complex number z, I will give the meaning of e to the power z. Once I have the meaning of e to the power z, of course, for that I need some machineries, like I need the notions of analytic functions, I need the notion of differentiability, I need the notions of what is called power series. Then only I can kind of give the meaning of e to the power z. Once I have the meaning of e to the power z, then you replace z by just I theta. That means you will have the meaning of e to the power I theta. So therefore, one hand I have the meaning of e to the power I theta, and another hand in the right hand side I have a complex number. So that means I have to somehow conclude that these two complex numbers are same. And answer is yes. So for the timing, you just assume the Euler's formula e to the power I theta is equal to cosine theta plus I sin theta. With that assumption, you will have the representation exponential form of a complex number. Later on, when I'll kind of define the notions of power series or Lorentz series, then I will have the meaning of e to the power z, okay, as a function, okay. If I replace z by I theta, then it will give you some value, e to the I theta, and right hand side you have a value cosine theta plus I sin theta, then I will show that these two values are same. That means I will prove the Euler's formula. Okay, so that is very nice actually, that one can ask. So therefore, for the time being, you assume that to have the exponential form, but later on when I will give the notions of e to the power z, then by replacing z by I theta, then your e to the I theta, the way you know, like cosine theta plus I sin theta, the same value is same as the when I will talk about in terms of power series. Okay, So, or exponential function, we will talk about that. That is one comment. Okay, so this is one kind of observation, that what is the geometrical interpretations of multiplication of two complex number. Again, you can check it. It says that I am considering two complex numbers Z1 and Z2, both of them non-zero, and both will have a like trigonometric representation, R1 times cos theta 1 plus I sin theta 1, and Z2 is R2 times cosine of theta 2 plus I sin theta 2. Then what is Z1 times Z2? You just multiply it, use the trigonometric formula, sine and cosine. So therefore, you just, if I multiply it, it turns out is this one, and if I use the trigonometric formula, which is R1 times R2, this is cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. One can write this is cosine of theta 1 plus theta 2, and this is I sine of theta 1 plus theta 2. And if I draw a picture, what it will give is that, so this is my Z1, so this is my angle theta 1, this is my Z2, this is my angle theta 2, then Z1 times Z2, it's actually an angle, like it kind of increasing, or not increasing, it's kind of magnifying. So therefore, you have a complex number Z3, Z1 times Z2, so therefore what will be R? R is nothing but your R1 times R2, so it will multiply by the corresponding argument of the complex number Z1 and Z2, and what will be your angle? Angle will add up. Okay, so if the argument of Z1 is theta 1, argument of Z2 is theta 2, then your argument of Z1 times Z2, which is nothing but theta 1 plus theta 2. This is the geometrical interpretations. Okay, so now you have kind of one what is called equation. This is small arc of Z1 times Z2 is equal to small arc of Z1 plus small arc of Z2. What is the meaning of that? So you can say that, because you see, just now I have said that given a complex number, small arc of Z is a set. So that means this equality means actually that set equality. But what is the meaning of that? You have one set, you have one set, you have one set. Three sets are there. So what is the meaning of the equality? So equality is the following. You see, I have written. So suppose this equality, if I say, what is the meaning? The above identity is to be interpreted as saying that if values of two of these three multi-valued arguments are specified, then there is a value of the third such that the above equality holds. What does it mean? That means this is a set, this is a set, this is a set, right? So if I take one member from this set and another member from this set, then the equality mean is that I will have one member from this set such that the value is same as the sum of the values. So that is the meaning. Okay. So that means if I have this equality of small r, I will say that three sets are there. One set is equal to another set plus another set. So that means if I have A is equal to B plus C, right? What is the meaning of that? It says that you take two elements from any two sets, either from AC or BC or AB, whatever it is. If I choose, I have three sets. So if I take, say, small a from A and small b from B, then this equality means is that there exists a C in C such that your A is equal to B plus C. That's the meaning actually. So out of three sets, fix any two elements from that set, then there exists element from the third set such that this equality holds. That's the meaning. Okay, that's exactly I have written in the red color. So one example, for example, if I have 3. Now 3 will have exponential form. What is that? R times e to the I theta. So R is 3, and what is I theta? I theta means theta is 0. So therefore e to the power 2 pi I. Okay, I can. So if 3 has, so I am assuming that suppose 3 is of the form R e to the I theta, then 3 times e to the power 2 pi I. Minus 2 is equal to 2 times e to the power 3 pi I. And what is the product? 3 times minus 2 is minus 6. So then I am saying that since small arc of 3, it is specified. What is the angle? Angle is 2 pi. Small arc of minus 2, what is the angle? 3 pi. This is specified. So that means two members from two sets are specified. Then it says that there exists a theta 3 which is 5 pi, one of the values of argument of minus 6, plus a suitable multiple of 2 pi I can take, so that this identity should hold. So therefore, if I have 3 and minus 2, suppose if it is 3, if it is minus 2, so and 3 and minus 2 already specified one value of the one value from the argument set. So this is 2 pi and 3 pi. Then it says that minus 6, which is of the form e to the power I times pi 3, and pi 3 is exactly equal to your 3 pi plus 2 pi. This is 5 pi. This is one of the value, and that's how equality. So therefore you can say that 5 pi, which is 2 pi plus 3 pi. That's what, because 2 pi is a member from this argument of 3. So this is an argument of 3. This is a member of small arc of minus 2. Then 5 pi is a member from small arc of minus 6, so that 5 pi is equal to 2 pi plus 3 pi. That's the meaning of this line. Okay, yeah. Okay, but there is a kind of very interesting fact is that in the above identity, if we replace small arc by capital arc, then the identity is no more true. So that means what I'm trying to say is that, can I replace this small arc by capital arc? That means, can I say that capital arc of Z1 times Z2, which is same as capital arc of Z1 plus capital arc of Z2? Answer is no. Small arc is okay, but even then, when I am talking about the equality of small arc, then you have to understand in which way and in what sense I am talking about the equality. I am saying that this arc is same as this plus this small arc. That means you take or you specify any two values from any two sets, then there exists a member from the third set, so that equality true. In that sense it is okay. But if I replace small arc by capital arc, but capital arc is a kind of single valued functions. So therefore I am demanding, is it true that if I have two complex number, if I product it will be another complex number, then you can calculate its principal argument. Is it the same as the principal argument of its individual, sum of the principal argument of the individual? Answer is no. So in general it is no. So small arc of Z1, Z2 is not equal to small arc of Z1 plus small arc of Z2. And then you can easily calculate why. So look, so just try it. For example, yeah. So consider, say Z1 is equal to say I, okay, and say Z2 is equal to say minus 1, okay, correct. So this is my point I, and say this is I, and this is say minus 1. So first, what is the principal argument of say I? What is the principal argument? Principal argument with this angle, that means pi by 2, okay. And minus 1 is here. So what is the principal argument of say minus 1? This is actually from here to here. So that means this is pi. Okay. So principal argument of I is pi by 2. Principal argument of minus 1 is pi. Okay. But if I multiply Z1 times Z2, what is the complex number? I times minus 1. That means this is minus I. Right. So therefore if I have a complex plane, so this is my minus I. Right. What is the principal argument? Principal argument of minus I, that means I have to have the angle from positive real axis, but this time I will have anti-clockwise direction. That means this should be minus pi by 2. Right? So therefore, now you see, so that means you can say that, so capital arc of I times minus 1, which is what? Which is minus pi by 2, which is not equal to argument of I plus argument of, let's call minus 1. And what is that? Principal argument of pi. This is pi by 2 plus, so this is, so that means this is same as pi by 2 plus pi. Okay. So pi by 2 plus pi, which is not equal to minus pi by 2. So I have example of two complex numbers Z1 and Z2. Z1 is I, Z2 is minus 1. Z1 times Z2 is minus I. Principal argument of minus I, which is minus pi by 2, which is not equal to principal argument of pi plus principal argument of minus 1, which is same as pi by 2 plus pi. So therefore the equality, principal argument, which is no more true. Okay. But small arc is true, but provided in that sense I have discussed. So pick two elements from out of three sets, pick any two elements from any two sets, then there exists element in the third set such that this equality is true. Okay, so this is nice. One more comment. If I have a non-zero complex number, and if it is like exponential form is r e to the I theta, then if I have 1 by z, which is 1 by r e to the I minus I theta, so therefore small arc of 1 by z, which is minus of small arc of z. Okay, and you will have this equality, small arc of z1 divided by z2, which is small arc of z1 minus small arc of z2. Again, this is a equality, set equality. That means out of these three sets, so one set, second set and third set, out of these three sets, first fix any two elements from any two sets, then there exists element from the third set, so that this equality is true. So in that way. Okay. Okay, so now I will come back to the what is called power of complex number. So given a complex number z, and if it is of the form, say, exponential form r e to the I theta, then you can easily calculate what is called power of the complex number. So okay, let z be a complex number, n is an integer. If z is 0, of course, if I take any power z to the n, it is a 0. If z is non-zero, suppose it is the corresponding exponential form, and if I use the exponential property like e to the power t1 times e to the power t2 is equal to e to the power t1 plus t2, that property I am assuming for the time being, this is true, then by mathematical inductions one can easily prove that z to the power n, which will also be a complex number, but what is the corresponding exponential form? This is nothing but r to the power n e to the power I n theta. I have written. So if z is non-zero, then setting z is equal to r e to the I theta, and using the fact that exponential function c to the power t1 times c to the power t2 is equal to the power t1 plus t2, then by mathematical inductions one can prove that z to the power n, which is r to the power n times e to the I n theta. This is for n is 0, 1, 2, 3, that means natural numbers including 0, and if n is a negative integer, you just replace m is equal to minus n, and the fact that 1 by z to the m, which is z to the power minus m, if I use that one, then also you can prove that z to the power n is equal to r to the power n e to the I n theta. Okay, same thing. So that means if n is an integer, then you can have the meaning of z to the n, which is r to the n e to the power I n theta. Okay. Now it says that if I take in particular r is equal to 1, then you will have e to the power I theta to the power n. So if r is equal to 1 means what? You have a z is equal to r e to the I theta, na? So that means e to the power I theta in the left hand side to the power n, which is same as e to the power I n theta. Now what is that? This is a well known formula that is called de Moivre's formula, that you know, right? So cosine theta plus I sine theta, so you can think about this is by Euler's formula what? Cosine theta plus I sine theta to the power n, which is exactly equal to, what is that? This is another complex number, no? So this is cosine of n theta plus I sine of n theta. This is the de Moivre's formula you know. So therefore, using the powers of complex number, you can have it. So rewriting it, we get the following de Moivre's formula. So the left hand side, so this will give you cosine theta plus I sine theta to the power n, and it is exactly equal to, from the right hand side, cosine of n theta plus I sine of n theta, n running over z. Okay. So one example I have given, so root 3 plus I to the power 7. First you write it in terms of exponential form. It is 2 e to the power I pi by 6. And what is that form? So this is 2 to the power 7, then I 7 pi by 6. And just I am saying that this is, I am writing and just producting it. So this is 2 to the power 6 times e to the I pi, then 2 times e to the power I pi by 6, using the formula e to the power t1 times e to the power t2 is equal to e to the power t1 plus t2, and it turns out that this is actually minus 64 times root 3 plus I. Okay. Okay, so now come back to roots of unity, nth roots of unity. So this is again kind of many of you are familiar with that. So okay, so what is that nth roots of unity? That means I want to solve equations. What is that equations? So you have a equation says z to the power n is equal to 1. I am saying that what are the solution of this equation? That means, can you tell me the complex numbers which satisfies this equation z to the power n is equal to 1? Or can you please tell me one complex number so that if I take the nth power I already discussed what is the meaning of that, then it turns out that it is exactly equal to the value 1, where n is a positive integer. So how many values of z's are there? So like, is it infinitely many? Is it finitely many? How many? So the solutions of the equation z to the power n is equal to 1, it will have n many distinct solution. Okay, and how to do that? Since I have a exponential form, you can see I can easily calculate it. Okay, so the aim is that find the solutions of the equation z to the power n is equal to 1. Okay, how to do that? Now, so that means I want to find a complex number z which satisfies. That means if I take the nth power, it will give you 1. Okay. Now, since z is a complex number, so assume that it will have an exponential form. So let it be r e to the I theta, be a solution of z to the power n is equal to 1. I have to find what is my r and what is my theta. Okay. Now, z is equal to r e to the I theta is a solution. So that means r e to the I theta, z to the power n is equal to 1. That complex number should satisfy, and z is equal to r e to the I theta. That means r e to the I theta to the power n is also should be 1, right? But that is also clear that if I have z to the power n is equal to 1 and z is equal to r e to the I theta to the power n, but just now I have discussed the formula this is same as r to the n e to the power I n theta, which is exactly equal to 1, right? That's I have written. So therefore z to the n, which is r e to the I theta to the power n, which is same as r times n times e to the I theta to the power n, which is same as r to the power n times e to the I n theta, which is 1, and 1 I can write it as 1 times e to the I 0. So now I have a left hand side one complex number, right hand side one complex number. When two complex numbers are equal, the corresponding what is called r theta, if I suppose one complex number of the form r1 comma theta 1, another is r2 comma theta 2. The complex number equal means r1 is equal to r2, theta 1 is equal to theta 2. Or say x1 y1 is equal to x2 y2. Two complex numbers are same. If and only if x1 is equal to x2, y1 is equal to y2. Same thing. So I have two complex number. So this is Rn e to the I n theta, which is same as 1 times e to the I 0. This will imply that your r to the power n is exactly equal to 1. This is the modulus part. And what will be your theta? Theta will be in the left hand side n theta, which is nothing but this is I times 0, 0 plus 2k pi, where k is an integer. So that follows from the equality of two complex numbers. Okay. Once I have that, then we get n distinct solutions of z to the power n is equal to 1. And what is the solution? So k should start from 0 up to n minus 1, because once I take k is equal to n, then it is the value is exactly equal to k is equal to 0. If I take n plus 1, the corresponding value will coincide with the value with k is equal to 1, so on and so forth. So therefore we will have all n many distinct solutions for the equation z to the n is equal to 1. And what is that solution? You can write it explicitly, because you see r to the power n is equal to 1, right? And r is positive. So what is the value of r? R is 1. Okay, and what is the value of theta? Theta you can get it now. What is theta? So theta is equal to 2k pi by n, and r to the power n is equal to 1. This will give you r is equal to 1. So therefore what is the form? Z. So z is of the form e to the power I theta. Theta means 2k pi by n, and this is the corresponding. Okay. If k varies, the corresponding solution varies. But how many k's will vary? Only finitely many. That means finitely many distinct solution will be there. K will vary from whole integer, that's okay. But my point is that only finitely many distinct values will be there, because if k takes the value n, then your z n, which is same as z0. So if I write it as zk like this one, z suffix k, which is e to the power I 2k pi by n, then z0 is same as zn, z1 is same as z of n plus 1, so on and so forth. So therefore I will have only n many distinct complex number which satisfies the equation z to the n is equal to 1. K will vary on the whole integer, but it doesn't matter, only n many distinct values I will get. So therefore the equation z to the power n is equal to 1 will have n many distinct solutions. And what is that? So as I said, so you can easily write it. So since it depends, right hand side depends on k, so I am writing it as k. So therefore your zk e to the power I times 2k pi by n, which is cosine of 2k pi by n plus I sin 2k pi by n. Just by de Moivre's formula we know, where k running from 0 up to n minus 1 is called the nth roots of unity. Now each zk I can write what is called in terms of primitive. What is primitive? It says that, okay, I am setting your omega n, which is e to the power 2 pi by n, and then using de Moivre's formula, each zk I can write it as z0 is nothing but 1, z1 is if I write is omega n, this is omega n, z1, z2 is omega n square, z3 is omega n cube, and what is finally zn? This is omega n to the power n minus 1. In this way you can write it. So therefore I have a n many distinct solution of the equation z to the power n is equal to 1. These are the complete solutions, and I can write this solution in terms of what is called primitive of nth roots of unity. So I am saying that consider omega n is equal to e to the power I 2 pi by n, which is primitive nth roots of unity. Then using the de Moivre's formula, then nth roots of the unity, that means nth roots of the equation z to the power n is equal to 1, I can write in terms of nth roots of primitive. That means this is 1 omega n square, omega n cube up to omega n to the power n minus 1. So therefore you can say that z to the power n is equal to 1, it will have n many distinct roots, which are actually, you can write here z0, z1 up to zn minus 1. Okay, this is the roots. That set of roots I can also write in terms of primitive. That means this is same as 1 omega n up to omega n to the power n minus 1. Same, z0 is nothing but your 1, and then I am saying z1 is nothing but omega n, z2 you can say that this is the kind of formula, zk, which is nothing but it is omega n to the power k. So this is the relation. Okay, so therefore this is nth roots of unity. Sometimes I am saying that 1 to the power 1 by n. So this is the notations. That means I want solution of the equation z to the power n is equal to 1. Okay. Okay, this is like kind of geometry. Okay, how, like for example, if I take n is equal to 1, so z, so only one, how many points are there? Okay, or if I take n is equal to 2, so that is why. So you see, geometrically nth roots of unity are equally spaced points that lie on the unit circle mod z is equal to 1 and from the vertices of a regular polygon with n sides. So that means it says that if I take mod z square is equal to 1, okay, oh sorry, if I take z square is equal to 1. So that means what are the complex number? It satisfies these properties. If I consider the circle which is mod z is equal to 1. Now what is mod z? Mod z is equal to 1, z is equal to x plus iy, z is equal to x plus iy. So what is mod z is equal to 1? That means it says that mod z square is equal to 1, correct? And what is that mod z square? That means x square plus y square is equal to 1. That means it will give you a circle of radius 1, center 0. So this is my circle. I am saying that this mod z is equal to 1. Then what is the solution of this equation? Z square is equal to 1. You will have only 2 points, 1 and minus 1. So instead of z square, if I say that zq is equal to 1, what are the solutions? It says that equal, you see I have written equally spaced points that right. So that means you have 1 point here, 1 there and there. What is 4? 4 means you will have this equally spaced, this. This is the geometry. And what is the 5? So this is the corresponding this thing. So therefore you will have nth roots of unity are equally spaced points that lie on the unit circle mod z is equal to 1 and from the vertices of a regular polygon. So therefore you just make a regular polygon and the vertices will give you the corresponding roots of the equation z to the power n is equal to 1. That's the geometric property of the nth roots of unity. Okay. Okay, the same concept you can transfer in the context of what is called, instead of nth roots of unity, instead of 1 to the power 1 by n, if I have w to the power 1 by n, okay, where w is another complex number. So in other words, I am trying to solve the equation z to the power n is equal to w, where w is fixed complex number. What are the roots? Okay, same trick will work. Earlier you will have 1 which is of the form 1 times e to the power I0. Here you will have a fixed complex number and it will have a what is called exponential form. You just replace the same technique in this context, you will have the roots. So just for kind of very briefly, so maybe next time I will explain once again. So I want to find the solution of the equation z to the power n is equal to w, where n is a positive integer. You apply the same method. Earlier you will have z to the power n is equal to 1. So now I want to find what are the elements z which satisfies this equation z to the power n is equal to w, where w is fixed. Now so that means since z is a complex number, it will have exponential form r e to the I theta. So that means assume that it is a solution of the equation z to the power n is equal to w, and w is a fixed complex number. So let it be rho e to the I phi. This is the corresponding exponential representation, exponential form. So therefore I want z which satisfies these properties, z to the n which is same as r to the power n e to the I theta, which is w which is same as rho e to the I pi. Now I have two complex number, both of the kind of exponential form I know. So these two complex number equal, corresponding I can conclude that r to the power n is exactly equal to rho. And what is the relation between theta and phi? So here your n theta should be phi plus 2k pi. So this is the relations. So if I have r1 e to the power I theta 1 is same as r2 e to the power I theta 2, this will implies r1 is equal to r2, and what is the relation between theta 1 theta 2? Theta 1 minus theta 2, they should divide by 2k pi. That's the meaning. Okay, so I am using, so left hand side I have r to the power n e to the I theta, right hand side I have rho e to the I phi. So these two complex numbers same, that means this will implies r to the power n is equal to rho. And what is the relation between n theta and phi? N theta minus phi, it should be a difference, it should be exactly equal to 2k pi, where k is running over integer, and this is the solution. You can get it. And the rest of the part is trivial. Why? Because r to the power n is equal to rho, so what will be r? R is rho to the power 1 by n, that is perfectly alright, because z is equal to r e to the I theta. I have to find what is my point z, so this is okay, and you will have these equations. From here you can have the values of theta. Your theta will be phi plus 2k pi divided by n. So therefore your z case will be like this one. But as again, even though k is running over the full integers, but you will have only n many distinct zk's, because if I take k zn, which is exactly the value will be z suffix 0. Similarly zn plus 1, which is same as z1. So therefore even though k is running over full z, but I will have only n many distinct z which satisfies the equation z to the power n is equal to w. And what is my zk? Zk is exactly equal to this kind of form. Now you see, if I replace w by 1, then you will end up with the earlier one. because if w is equal to 1, then your rho will be 1 and phi will be 0. So therefore you will have the nth roots of unity. Okay, so here k running from 0 up to n minus 1. Now there is another kind of fact, earlier one, like in terms of primitive I can write all the nth roots of unity. Similarly, if c is any nth root of w, any point, so either z0, z1, whatever it is, then all the nth roots of w you can write it as c omega n square up to c omega n to the power n minus 1. What is my c? C is any root of the equation z to the power n is equal to w, and what is omega n? Omega n is the nth roots of or primitive of like earlier one, z to the power n is equal to 1. So therefore, if c is any nth root of w, then all the nth roots of w can be written as c omega n up to c omega n to the power n minus 1, where omega n is the primitive nth root of unity that I have discussed in my last slides. Okay. So one example, so like if I'll ask you that what is the cube roots of 64 times I this complex number, then you can say that, okay, so if a cube roots, that means it will have 3 distinct values will be there. I am talking about cube. So this is my z0, one value, this is my z1, and this is my z3. Formula is there, so you can just like you have to solve it. Okay, so earlier one you will have z to the power n is equal to 1. Now this time you will have z to the power n is equal to 64 times I. Okay, so since I am talking about cube roots, it will have 3 distinct values, z1, z0, z1, and z2, and which is exactly of this, this, and this. So you have this formula. You just write in terms of exponential form, equate it, and you can do that. Okay, I leave it as an exercise. So I have written it. What are the cube roots of 64 times I? This is my z0, this is z1, and this is z2. Yeah, this should be, I think, z2, not z3. This is z2. There is a typo. Okay, this is z2. You can calculate it using this formula. Okay. Okay, so one last slides. So this is my done. I think I should complete it this one. Okay, so this is, so nth roots of unity I have done. Now nth roots of non-zero complex number, that is also done using the same formula. Now if I am asking this kind of questions, computing the value of w to the power alpha, where w is non-zero and alpha is rational. Now look here. So I have a w is a non-zero complex number, okay, and then I am talking about what is w to the power 1 by n. Now I am replacing this question w to the power alpha, where alpha is rational number. That means I am trying to calculate w to the power p by q. But that's also I can do that. Why? Because I can say that this is same as w to the power p to the power 1 by q. That I can do. And if since w is a complex number, I can have w to the power p, this is another complex number, and I am trying to find what is the qth root of this w to the power p. So that's how you can calculate the w to the power alpha, where alpha is rational. Okay, so w is a non-zero complex number. Suppose alpha is rational, it is of the form m by n, where m and n are integers, GCD is 1. Then w to the power alpha, I can write it as w to the power m by n. And what is that? This is same as w to the power m to the power 1 by n, right? Now, if w is a complex number, w to the power n, you can calculate it, right? So that is another complex number it will give. So then what I am trying to do is that I have to find the nth roots of w to the power m. Okay, since m is an integer, w to the power m will be a single complex number, and then taking the nth roots of w to the power m, will have n distinct complex numbers zk, which satisfies this one. So same thing, it's very nice. So therefore, even though it is a kind of what is called rational number, but that rational number, if I write it of the form say p by q, then what I am doing is that I am considering w to the power p to the power 1 by q, and what is that? This is say w twiddle to the power 1 by q. That means I have to find the qth root of this new complex number w twiddle. What is w twiddle? This is w to the power p, and that you can easily calculate it. Okay, so this is one exercise. I'm telling you, you please calculate it. How to handle this situation? This is minus 8i to the power 2 by 3. Then how to proceed? That means you have to do minus 8i to the power square to the power 1 by 3, right? Now this complex number you can easily calculate. So this is 64, I think. This is a 64, and this is, yeah, minus 64 to the power 1 by 3. That means to get the values of this, you have to calculate the cube roots of minus 64, and this will be the values of this one. Okay, so therefore, if I want to give some exercise saying that calculate or computing w to the power alpha, you should not scared. What you have to do, you just that fraction or like rational, you just manipulate. This is nothing but take the power and take the 1 by 3 or 1 by q, whatever it is. So then get a single complex number and then talk about what is called its corresponding third root of that complex number or corresponding qth root of this complex number. Okay, so I think that is all about like nth roots of unity and properties of complex number. So I think that's very like brief about my complex number and its algebra. Now since I have the concept of distance, in my next class I will talk about what is the topology of this complex number, like open set, closed sets. I will start those kind of concept in my next lecture. Okay, I think I should stop. Thank you.